This video will cover a variety of nomenclature issues regarding isomers and things associated with isomers such as conformation, configuration, and stereochemistry. Now with stereochemistry, we have something that is a very important part of a three-dimensionally shaped object, particularly if it's interacting with another three-dimensional object. These types of things can have a feature which is casually called handedness, and this relates to a typical hand which has 4 fingers and a thumb, right? Your right one is very similar to your left one, except for the fact that they're kind of like mirror images of one another. We're not talking about the little details of creases and everything, but just in general, the overall shape. And that being the case, we realize that even though they otherwise look identical, they can be distinguished from one another in that we can't superimpose the two of them. So they are unique, such as in a photograph or in a mirror or something, right? When we see something like that, things appear to be inverted, and in a photograph we can tell if it's in the right orientation. If we know, right, if something looks like it's on the opposite side of where it should be. Especially obviously when there's lettering and it's backwards. But if you can tell the difference between the right side of you and the left side of you, and you see it on the wrong side in a photograph, for example, you know that you are obviously dealing with an inversion of that image. So that's a lot of what we're talking about here, and so let's get on to this. So if we consider biological molecules, they usually have stereochemistry incorporated in their structures. If you remember from biochemistry, all amino acids are L-amino acids, and we'll talk about what that means. But that means that they have this feature that a mirror image of them will not be identical to that particular molecule. It'll look similar, except for it's like inverted in a mirror type of thing. Therefore, molecules which interact with such things also need to exhibit those types of features so that they can interact with such a structure that has this feature of non-superimposable mirror images. Okay, so we now have various types of what we call comparisons of compounds. So if we're comparing two chemical compounds, we can ask right off the bat, first of all, do they have the same molecular formula, right? Do they have the same number of carbons, hydrogens, oxygens, phosphorus, everything else that they may or may not have, right? If they do not have the same number of all of the specific atoms, then they're not isomers, and we don't have to worry about them. They're just very simply different compounds, okay? So we don't have any issue with regard to differentiating them based on that point. The molecular formula alone can tell us, oh, we have something different here. But if the molecular formulas are identical, then we have an issue. It's like, well, wait a minute, if they're not identical, how are they different? And there's different ways in which this difference can appear. So that's what this decision tree that we have here talks about. So first of all, if they are isomers, so we follow the vertical line, yes and down, and that's so they are isomers. The question is, what kind of isomers? You can see this branches out to two different types of isomers, constitutional isomers and stereoisomers. So to differentiate between them, the question that we have to answer is, do the compounds have the same connectivity? In other words, of all of the atoms that are in that compound, that compose the molecular formula, right? Are they all coupled in the same manner to one another in each of the two compounds? So an example where they do not is shown on the left here. We have 3 carbons, right? It'll have 8 hydrogens. So there's 3 on each of the two. If we look at the alcohol on the left, right, we have 3 on each of the 2 methyl groups, 1 on the methine, right? And then 1 on the OH. And we have the same in the compound on the right. Now the key difference that you see between the two is one is an alcohol and one is an ether. Well, they're very different compounds. They have different physical properties. they're going to have different boiling points and melting points, right? So they're clearly different compounds. And how are they different? They're different in that, for example, the oxygen atom in one case is only attached to a hydrogen and one of the carbons, whereas in the case of the other, the oxygen is attached to two carbons. So that's clearly a difference. The other thing is the compound on the left, right? We notice that the oxygen is attached to the middle carbon of a chain of 3 carbons, right? You can imagine even another constitutional isomer here where that OH group is attached to the end of that chain of 3 carbons, right? You can see we would have a primary alcohol then, and this is a secondary alcohol. So there's many different possible constitutional isomers we can have by simply attaching the atoms to one another in a different way. Kind of like you have the same number of bricks, right, in a Lego kit, and you can assemble them in different ways. And as long as they're not identical, right, you have made basically constitutional isomers of one another. Okay, so now if the connectivity is the same, right, then what we have are something called stereoisomers. Now again, we have either configuration or conformational stereoisomers. So the question becomes, is there a way that by the rotation of single bonds within this molecule that we can make them look identical? Okay, if we can do that, then they're conformational isomers. In other words, they're only isomers from the standpoint of the fact that a bond is rotated in them, right? They're not really different compounds in a sense. They're just same compound in a different shape, kind of like taking a piece of string and tying a knot in it or leaving it straight, right? It's still the same piece of string. It just has a different shape. That's what a conformational isomer is. If we cannot interchange these and make them identical by rotation, and let's just quickly kind of take a look at this, what we mean by this. So here we have a 4-carbon chain where it's extended. In other words, this carbon is as far away from this carbon as it can be. Whereas in this image of this molecule, we have this carbon attached to this, and then, but it's actually right now as close as it can be to that other carbon based on rotating this central bond here. So if we would take this compound, say for example, and take this carbon and rotate this 180 degrees, so it would actually be that carbon would be pointing up, right? We would get something again where the two carbons are as far away from each other as possible, and we would basically have the same compound. Actually, I probably should have used this carbon as the example because you can see how it would be exactly identical. So if we take this carbon, right, here, rotate this 180 degrees about this bond, this carbon will end up straight up here like where this is, right? And it'll in fact be this identical thing. So it shows that these two are the same molecule. They were just conformational isomers one another, and these are interchangeable. Okay, now if that's not the case, if we can't do that somehow with a molecule, then we call these configurational isomers. Okay, well, we have more than one type of configurational isomer. So again, our differentiating question that we have to ask is the isomerization at a double bond? Okay, if no, it's what we have called an optical isomer, where we're going to spend the next several slides discussing different aspects of optical isomers. But the other case, very simply, is if we're talking about a compound that has a double bond in it, we call these geometric isomers. Because what we have here is compounds that have this different geometry of, again, this carbon is as far away from this one as it can be, and this one is as close as it can be. But we cannot rotate this central bond. Okay, it's a double bond, this is planar, and it does not rotate. So these cannot be interconverted to one another because we cannot rotate that central bond. So they're clearly different. They're going to have different physical properties, and we call these geometric isomers. And you may remember some of the nomenclature for this would be called transbutene, and we might include the 2, so transbute-2-ene, indicating that at the 2 position, right, is where this double bond starts and it goes to the next, so it would be 2 to 3, right? And the same here, this would be called cis-bute-2-ene. So again, the ene is here. Okay, so we have that, and that's then, we can clearly name these compounds and differentiate them. Now, for optical isomers, we have what we call enantiomers and diastereomers. So the real simple thing is, right, notice there's a definition here we have for enantiomers. Are the compounds non-superimposable mirror images? This is what we talked about like with our left and right hand, right? They are non-superimposable mirror images. So they are enantiomers. So this is, I mentioned the term earlier, this is what we mean by that. And this is a chemical compound showing that you can imagine that there's a plane of symmetry going right between these 2 compounds. And you can see this chlorine matches with this methyl matches with this hydrogen matches with this, and this ethyl group goes back and it's on the opposite side over here, right? It's completely symmetrical. But no matter what we try to do, if we try to put one of these, in a 3-dimensional way over the other one, we will find we'll always have a mismatch of 2 of the groups. No matter which 2 groups we match up, the other 2 will mismatch. Okay, so imagine taking this compound here, right, matching up the chloro and matching up the ethyl group, right? So in order to do that, what we would do is we would look at this axis axis where the carbon chlorine is, and we would rotate this compound 180 degrees, right? So what it would do is it would take this ethyl group here and rotate it all the way around to the opposite side like we have here, right? So what does that also do to these? Well, this carbon, if we rotate this 180 degrees, is going to end up right over here and behind. So it would have a hatched arrow, and this would be rotated around and coming up over here, and it would be a wedge to a hydrogen. So what it amounts to is, what it would be is you would have the chlorine and this ethyl in the correct place, but you would have a CH3 here and a hydrogen here. So clearly they do not overlap with one another if we do that. And that's just from rotating the compound, just like you would turn your hand. Still the same hand, nothing else has happened to it. You're just looking at it from a different angle. So that's what we're talking about, that we cannot superimpose these. Okay, so that is the definition. You should know that definition. That's basically all you need to know with regard to these. And the other aspect here is we'll talk about the designation for the stereochemical centers here. To have enantiomers, what's going to happen is whatever designation we have for these stereochemical centers, all of them in the compound, say if there's more than one, have to be the opposite. So we'll explain this again later, but that's another just general rule of thumb, that every stereocenter has to be inverted in an enantiomer. In diastereomers, right, all it is it just basically fails this message. So in other words, generally they're like not mirror images of one another to start with. Okay, so yes, they're non-superimposable, but it doesn't matter because they're not even mirror images of one another. Okay, they don't have that symmetry characteristic. So those would be diastereomers. Now, there's nothing magical about these terms in that both of these terms don't exist on their own, right? A single compound is not either an enantiomer or a diastereomer. Enantiomers are only enantiomers when we're comparing 2 compounds and we're comparing the features of those 2 compounds to each other, right? It's not an inherent property of a single compound. So that's an important aspect here. The important aspect is that it is a comparison between two compounds. The same is true for diastereomers. So we'll show examples of, say, a group of compounds where we have pairs of enantiomers and all the other combinations other than those pairs are diastereomers of one another. And they're all the same compounds. So we'll show that example. Okay. Now, within constitutional isomers, right, remember we talked about, if we go back here, right, constitutional isomers, right, we were talking about these compounds here. So they're connected in different ways. Now there's another way in which this can occur, and that's something which we call tautomers. And this is compounds that are rapidly interconverted to one another. And it usually involves the movement of some atom and bond or bond. But they can rapidly interconvert back and forth. And so we often don't have only one of these present. Sometimes even if we had the pure compound to start with, there would become some population of the other. The next slide will actually show some examples of this. Okay? And then remember, when we say stereoisomers, we're talking about two different things. We're talking about the configurational isomers and conformational isomers, right? So the configurational, the ones where we're going to have our designations of stereocenters, okay? And our conformational isomers are those that we can interconvert by twisting bonds. So again, we can go back and orient ourselves with this previous slide and see what it is, right? This is what we're talking about. Stereoisomers has either configuration or conformational. Okay, so if you compare these two slides, you can see what we're talking about. The only thing that wasn't mentioned on here are these tautomers. Okay, so what's a tautomer? A tautomer is two different species of a different chemical with different chemical bonding patterns, right? So that makes it different pattern, right? Is a constitutional isomer. Okay? So if we look in the top right and we have a ketone, right? It's got a carbon, some other type of carbon element, a carbonyl group, C double bond oxygen, right? We call that functional group a ketone. Now ketones have sometimes the ability to exchange a proton that is next to the carbonyl group, put it on the oxygen, and the double bond, so the electrons from the double bond of C double bond O go between the carbon and the carbon. Okay? So what is actually happening here? An H minus, you can think of it as an H minus, right, is going onto the oxygen. And so to not have a minus charge on the oxygen, the electrons of this bond go down here. And it makes a neutral compound again, because if we lost an H minus here, this would give a carbon plus, right? So that being the case, the double bond here coming down neutralizes that. So we get a compound that is also neutral. It's called an enol, so ene, double bond, that with an OH directly attached to it. And so there's a name for this called keto-enol tautomerization. Now, in the case of different ketones, right, there'll be different proportions of these. And a lot of it has to do with the acidity of this proton, as well as if there's any stabilization of this OH out here. And there can be various ways to do that. Hydrogen bonding is one. We'll talk about molecular interactions and things like that later. But if we stabilize this structure, then we can get, say, more of this than we otherwise might. So notice most of the time this arrow is longer going this way. There's more of the keto form. And in fact, the compound acetone, where this is a methyl group and this R group is also a methyl group, right? That's the compound we call acetone. It is mostly in the keto form, 99.999%, which means 0.001% is in the enol form. Okay, And we know this, and we can determine this by spectroscopy because the spectral characteristics and absorption characteristics of compounds such as this versus this are different, and they're quantifiable. So like in infrared spectroscopy, we're looking at the resonance of the bond strength of the C double bond O, which is not here, right? It's a single bond, so that resonance is going to appear at a different location. And then this doesn't have a C double bond C. This does. That has a different resonant frequency. So it would appear for this compound and it wouldn't appear for this. So what it means is our spectra, right, would have bands associated with the ketone, this carbon-carbon and the C double bond O, constituting 99.999 strength greater than the strength of the absorptions we see for the C double bond C and the C single bond O. Those things which are not present in this. So the spectra would have both of these, but at different proportions. And that's how we can get a sense of how much of each of these that we have in a structure. There's other types of spectroscopy that can be used as well, but that's just one simple example that you might remember. Okay, then we have imines. An imine is nothing more than a carbon double bond nitrogen molecule. And it's usually formed by having a ketone and an amine coming together through the loss of water. Okay, so that's just chemically how it happens. But imines are compounds, and this is showing what it looks like. And similar to what we have with the ketoenol, right, we can have an ene-amine, which is a double bond carbon-carbon attached to an amine. Now these have different types of stability, different levels of stability, and so in many cases we can see different proportion of these that are significantly different from what we see in ketoenol, even for otherwise similar compounds, right? So this one has more of a tendency to form both of these forms than do ketones. And then our last example, which we have on this slide here, is nitroso compounds and oximes. Okay, so oximes are favored usually, and in fact, you usually don't see things drawn in this form because the favored form is usually what we chemically draw when we make a compound, right? So we often don't draw both forms when we draw a chemical compound, and you just have to be aware that this is a feature. And in most cases, it's not too much of an issue. In oximes, it's mostly this. In ketones, it's mostly this. Depending on the compound that you're drawing, you might get one or more of these. Or it might just be drawn in one form that is viewed as being favored. And that's, again, possibly because in the spectra they observed more than one form than another. But in a very similar compound, right, it may favor the other form, and it might be then drawn the other way. Okay? So you have to take that into account when you see some of these things, that the other is possible. And we'll actually see ketoenol tautomerization in several types of things, particularly things like antibacterial drug tetracyclines. Well, it's actually an important feature of that. So we'll mention that when we have a chance. Constitutional geometrical isomers. So if we have pentane, right, which is just hydrocarbon with 5 carbons, we can arrange those in a straight line. We can branch it, and we can branch it in more than one way. And so we have names for some of these. If it's linear, right, we call it normal, or we do an italic N in front of it. If it's branched in this symmetrical way, we call it iso, and sometimes an italic I, or sometimes it's called secondary. And this, where it's as completely branched as possible, right, we call this tertiary, and it's an italic T, pentane. Okay? So you can think of it from the standpoint of, where this branching occurs. This is maximally branched, right? This has all carbons at all positions. This is going to be similar to what we're going to talk about tertiary for other functional groups as well, where basically it's substituted with carbons at all positions. We have iso, where essentially we have a CH and then branching for the other positions, right? So that's very often called secondary. And then normal, of course, is just linear again. So, I mean, we're going to see some variations of these terms used for other functional groups as well. Okay, in our cis and trans butenes here, another nomenclature that's often used is either E or Z, and they're based on the German word entgegen or zusammen. So cis corresponds to Z and trans corresponds to E. So you might see in nomenclature of a compound one or the other, and you should be aware of the equivalence of these two. Okay? Now in ring systems, we use the term cis and trans as well. We also, in these bicyclic systems, you might see these terms endo and exo. Don't worry about the endo and exo so much unless you get into natural products and some other types of chemistry. You're not going to see them too often. Okay, so, there's some certain compounds that could have medicinal value that have these types of things, but these are not encountered as often. But you do regularly encounter hydrocarbon rings that are, can substitute it in a way that's called cis or trans. So if we have a cyclohexane, right, it would normally look like this. It's 6 carbons that are tetrahedral, and if you make a tetrahedral structure in 3 dimensions, you'll see that it kind of makes this kind of puckered ring. It is flat for the most part, but it's kind of flat if you kind of look at it as an angle across it. And it has bonds or protons. Well, in the case of cyclohexane, all these hashed lines are where protons would go, the bonds to carbon and hydrogen. And you'll notice we have 3 that are above the ring, right? And then we have basically 3 that are below. Actually, this one's not showing the hatches. So back here, there's another one coming down. So 3 below the ring. And then we have 1, 2, 3, 4, 5, 6 that are in the plane of the ring. Okay? And so one way to depict these where we don't have to draw these hatch things, and this can be a little hard to draw sometimes. Often these things are flattened out like this, which means you're essentially looking down, say, from the top and seeing what you have. So in other words, if we have this compound here, it has 2 methyl groups on it, and we look down from the top, it will look like this in an image. So we would have a hexagon, basically, and 2 methyl groups coming from it. And one of which would be considered kind of either in front or not in back, basically, and the other would be considered in back or not in front. Okay, why do I use the 2 terms? Because remember what I said. Well, you have these are above definitely, and these are below definitely. These are in the plane, but if you look at how they are relative to each other, right? This one's above and in the plane. This one is below here and in the plane. So if we only consider a picture like this where they're either above or below, we're basically calling every other in the plane one either above or below, if that makes sense. So let's just look, say, at this one position, right? This is clearly below the ring. So if we're basically saying we can only have either above or below, we're going to have to say this one has to be above, right? So that's going to be represented by this wedge. At this position here, we can either have something that's above or below. Well, this is actually kind of in the plane with the ring, but we consider, since it's not above, that it is then going to be depicted as below. And that's kind of how all of this plays out. The nice thing about this is when we draw it in this projection form, so in other words, looking down from the top, like a, that's called a projection, a particular perspective of something like this, that we can very easily see that, oh, these are on the opposite sides of the ring. So we can use that idea of across from one another or near one another in the simplest of ways. So this we're calling trans, in that they're on opposite sides of the rings. And this one we're calling cis because they're on the same side of the ring. So what do we mean by the same side of the ring? Well, this one's going up, right? We give it a wedge here. And this one's not going down. So in a sense, it's on the same side of the ring as this other one. So we're calling this one cis. But in three-dimensional forms, this is what it looks like. So this is what a cis looks like, and this is what a trans looks like. And we would do the same thought process if we have, this is a 1-2 position. If we had a 1-3 position, it would be the same thing. Although it's a little bit easier to see, very simply because if we go from, say, this position to this position, right, it's either above, right, and they're pointing in the same direction, or they're not pointing above, so therefore they're below, and they're also kind of in the same direction, okay? So that makes it's a little easier to see when they're in the 1-3 positions. These 1-2 positions, you have to actually use a little bit of thought process in order to kind of see what they look like in 3 dimensions. Okay. So for configurational isomers, remember we had enantiomers and diastereomers. Now, both of these, the examples that we showed, are chiral. There is one unusual situation where you can have a chiral compound that has an additional plane of symmetry in it. And if that plane of symmetry makes the two halves of that molecule now be mirror images of one another, then we have what's called a meso compound. And it turns out technically that's achiral, because what you have is, if you take the mirror image of it, you say, oh, well, you're inverting that stereochemistry, but each half of that molecule is already an inversion of the other half of the molecule. So all you have to do is take the mirror image and rotate it 180 degrees, and you've now superimposed the groups that are now of the same stereochemistry in each place. We're not going to spend much time talking about meso compounds because it's not the type of thing we have to worry about. Well, first of all, they're achiral, right? So when we talk about stereoisomers and things like this, most of the time what we're going to be wanting to talk about are chiral compounds and their chirality. So even within this achiral compound, we can talk about certain aspects of stereochemistry, but it's stereochemistry relating to portions of the molecule, not the overall. Okay, we'll show an example and you can see. So in your DLOs, we talk about meso compounds, and it's not an unimportant topic, but in terms of focus, the important things to focus on are these chiral aspects, okay? And again, one thing you absolutely need to know are the definitions of how to differentiate between an enantiomer and a diastereomer. And enantiomers are merely non-superimposable mirror images. Okay, so they're mirror images. So if you think about it, everything that they do as a bulk property within themselves is going to be the same for the two of them. They would pack the same, so form the same types of crystals. They would have the same affinity for themselves, so their melting and boiling points would be similar, right? Obviously, the molecular weights and everything else is similar. The only physical property that they have, which is very distinguishing, is they can rotate they can rotate light as light passes through them. Okay? And they can rotate it either in a clockwise or anti-clockwise direction. Now, the two different mirror images that we have of each other, the two enantiomers, will be able to basically rotate that polarized light in different directions. So one would do it clockwise, one would do it anti-clockwise, and to equal degrees, right? Because the amount of rotation that we actually observe is a function of the concentration of the compound and the length that we are passing, the length of the solution that we're passing this polarized light through. In other words, as it goes through, it gradually turns and turns and turns and turns. So if we have a longer tube of this material, right, it will turn more and more and more. When we observe this property, we have to take into account all of these features such as concentration and length of the tube from which we're making the measurement of this rotation. Okay, but equal and opposite optical rotation. This is a characteristic that can be cataloged and put down for any particular compound, and it is characteristic of that particular compound, of that stereochemistry. Diastereomers, right, are not mirror images of one another. So they're actually different in some very different ways, such as the ways that, again, they could pack, interact with one another, so their melting points might be different. Might not be that different, but it could be. There's no necessity that they have to be the same as they are with enantiomers, okay? So they can be different, and their optical rotations, there's no rule as to what each of them can be, so they're going to be different in some way, shape, or form, okay? Now, when we're talking about chirality and naming what we call chiral centers in a molecule, which is nothing more than a center, it's an atom that has four things attached to it, four different things attached to it. When we have that, we have what we call a chiral center. Now, most of the time, we're talking about carbons as chiral centers, but we can have other atoms. So, for example, sulfur, if we have a compound that is a thioether that has two different substituents on it, and we oxidize one of the lone pairs of electrons to make a sulfoxide, that can be chiral. When there are two forms that are formed, one of them would be in one form and the other is its mirror image. Okay. So if we're looking at differentiating two enantiomers based on optical rotation, we either call them dextrorotatory, which we symbolize with a small italic d, or levorotatory, which we symbolize with a small italic L. Or we get away from the Latin terms and we just use a plus for dextrorotatory and minus for levorotatory, right? Dextro is right, levo is left. So plus and minus terms are very commonly associated with that. Okay, now, we can have our amino acids, which we normally talk about. Our 20 mammalian amino acids are all L configuration. What we mean by this is these are designated with a capital D or a capital L. So you may hear about D-glucose or L-alanine, this type of thing. That's the nomenclature that's used for those compounds when we hear those names. And these are not systematic in a sense. These are named based on their chemical relationship to a defined standard compound. So historically, right, there is a standard compound that somebody knows the three-dimensional structure of, and it was just discovered by some particular means, right? And rather than having to go through the arduous process back in the day of figuring out what was the actual relationship of all of these atoms to one another in terms of the two possible mirror images, which before the days of crystal structures was a lot more work, Here, we could just simply say, well, if we can interconvert chemically our compound into something that we know the stereochemistry of, or we convert it into something that has the opposite stereochemistry of a compound that we know, we can define the chirality of that compound, right? It's very simply that. And that has actually been a tried and true method that has been used for many, many years. In fact, I actually did it for my thesis. I proved the stereochemistry of one of the compounds that I was making by this method. So it works. It's very interesting, and but it's a lot of work. It's easier to name chemical compounds if we have a systematic means of naming that has. We don't need to make an optical measurement, right? We don't need to compare it against another standard. We can just simply look at the structure the way we look at UPAC, right, and name compounds. And we can basically set up a set of rules that say, well, if we see something that looks like this, and in this type of diagram, the OH is coming towards you, the hydrogen's coming towards you, these other two bonds are going away, right? Here's the central carbon, this OH is coming towards you, this hydrogen's coming towards you, and that's going away. So this is actually a three-dimensional projection depiction that's understood in a very standard way. And what it amounts to is we could look at this and say, okay, let's develop some rules that just by looking at this, we can tell you exactly what the stereochemistry is of this position and this position, because these are our two chiral positions. And that's what we have with the Kahn-Ingold-Prelog system, which is part of UPAC and used for chemical naming. And that gives us these R and S configuration determinations for these different positions. So that's our R and S system is formally known as the Kahn-Ingold-Prelog for the people who determined and basically came up with the rules for this system. So this is a depiction of how we actually determine stereochemistry using the CIP or Kahn-Ingold-Prelog rules. So the top is the traditional thing, and actually this is printed in the original UPAC rules and the papers associated with that. So this is the diagram that they actually use. And what it is you've a chemical compound that has a central atom. It happens to be a carbon that's being shown here, but we could talk about it as anything else. And then it has four different things attached to it, right? And it's in a tetrahedron. What we do is we look at it and determine the priority of those four different substituents based on the atomic number of those four different substituents. So here we're saying, in this case, A is greater than B, is greater than C, is greater than D. Okay, and we look at a periodic chart, look at the atomic number, and say, okay, we know which is which. So that's what determines priority. Then what we do is we take the atom with the lowest priority, which in this case is D, and we orient it in a line directly away from the direction that we're looking. So that's why it's showing a picture of an eye looking to the left, and then the carbon D bond, right, goes off to the left, farthest away from the eye. And what you see then is a projection of ABC arranged right around like a tristar, right? And they would be arranged in such a way that if we go from A to B to C, right, it'll either be going in the clockwise or anti-clockwise direction. So if we look at the top one on the left, if we look at A and it goes to B, that's going behind, and then it's coming around underneath to C, and then back to A. And what that is that's the clockwise direction. So since this is going in a clockwise direction, we designate it as R configuration. Now in this compound, right, here's our D, here's our A, B, C, but notice now to go from A to B to C, we're going around in an anti-clockwise direction. So we call that S. And notice it's usually a capital R and it's italicized, and it's a capital S and it's italicized. Okay. So here in the rest of this figure, I don't have them italicized properly. They really should be. But a lot of times you'll see them without being in italics. So this is just another depiction, and instead of using priority of A, B, C, D, what we're going to do is using just a numbering system of 1, 2, 3, and then the compound which we put to the back, I mean the atom which we put to the back, which has the lowest priority, which would be D up here, right, is going to be 4, right? So there's 1, 2, 3, 4, because there's only 4 substituents. Again, so now if we ignore the 4 because it's going behind, we get this tri-star here. And if we go from 1 to 2 to 3, it either goes clockwise, or in this case, it goes anti-clockwise. So this is S and this is R. Right? So our priority is 1, 2, 3, 4. Clockwise is R, anti-clockwise is S. Now, we have 4 compounds down here at the bottom, and we have already designated what their stereochemistry is. So the question is, okay, how did we get to this? And what's the relationship that we have between these different compounds, right? So all 4 of these compounds are actually different. They're stereoisomers of one another. So we'll talk about what they are and what the relationship. But first of all, let's just talk about what this is. So the numbering, the chemical numbering that we would have for this compound would put the hydroxyl group with the higher priority than the fluorine group. So that means that it's going to start out on the end of the chain as position 1. The position with the hydroxyl is going to have 2. The position with the fluorine will be 3. And the last methyl group will be 4. So from that standpoint, all of these other compounds would be numbered the same way. The only thing that you just need to pay attention to is look where the hydroxyl group is, right? It's here, here. These are okay. They're kind of in the same orientation. These on this side are flipped 180 degrees. And I did this for a very specific reason. You can imagine, let's just take these 2 structures on the left. If we put kind of a plane of symmetry straight up and down through here and took the mirror image of the left side and put it on the right, that mirror image is what we have for these 2 compounds. Right, so one pair of these is going to be a mirror image of each other, and the other pair is going to be another mirror image, and then some others are not going to be mirror images of another. And so we can talk about those terms in enantiomer and diastereomer. So before we do that, let's talk about these compounds with regard to how did we get to this R and S determination for these, right? So these are now a real example. So if we look at the compound on the lower right, we would assign this position 2. Remember, we said position 2 is where the hydroxyl group is attached. So this is carbon 2. So that's why we say position 2, right? So that's this 2R here, right? How did we get to this R? So the highest priority, and this is how we do the priority assignment. We'll look at, okay, we have 3 different atoms, right? We have, well, the hydrogen's the lowest, right? So that goes to the back. So we're going to ignore that because that's the lowest. We don't have to worry about it. Here, the oxygen is going to have higher priority than the carbon and the carbon, right? So it's going to get priority 1. So that's priority 1 is the oxygen of the hydroxyl group. So that's why we put this 1 up here. Now, if we compare this to this, we have the problem that this is attached to a carbon and this is attached to a carbon. Remember, we're only looking at one atom at a time in order to determine these priorities. So we march out and we say, oh, it's a carbon and it's a carbon. So how do we differentiate it? We do what's sometimes called as a tree diagram. So what it amounts to is this is kind of a branching. So, right, we in the first place, we were easily able to identify the priority of this over these 2. But now in order to get this, we now have to do a second step. So if we want to consider the branching, right, the branching goes out to what is attached to this carbon. Okay, well, the position here has a fluorine, a carbon, and a hydrogen. And this position here has a hydrogen, a hydrogen, and a hydrogen. So this one, which we're giving priority to, is priority 2 because this fluorine is the highest atomic number of all of the atoms we see here, right? And so that's all it takes. It takes this one atom of the highest priority to say this position, right, is higher priority than this position. So now we have the 3. We have 1, 2, 3, right? And it's clockwise, so this is R. So that confirms that our position 2 is R here. So now we have this other carbon here that actually has the fluorine attached to it. How would we assign that position? So we do the same process. We look at this carbon here and see what's attached to it. Okay, so it has a hydrogen. That's the lowest priority. It has a fluorine. That's going to be, as it turns out, the highest priority because the other two are a carbon and a carbon, right? This is a carbon, this is a carbon. So that's going to be the same type of a tree diagram situation. And so we give priority 1 here to the fluorine. Then we have 2 carbons, one of which is attached to an oxygen, a carbon, and a hydrogen, right? An oxygen, a carbon, and a hydrogen. Okay, so those are those 3 atoms. This carbon has 3 hydrogens attached to it, which we're not depicting, right, in typical way we draw chemical structures. We don't always draw the hydrogens. So this has the carbon with 3 hydrogens. So if you look at all of these atoms right here, oxygen has the highest atomic number. So it will get the next priority, which is priority 2. So this carbon gets priority 2, and then this by default gets 3. Now, notice we have a situation here, and we can do a couple of different things. The situation is our hydrogen here is facing towards us, and the fluorine is facing away. This is the opposite of what's required up here in order to determine, right, whether we have clockwise or anti-clockwise. So what we could do is we can mentally take this compound and turn it around so that the hydrogen's in the back and the fluorine's at the front, right? And then these 2 sides would be switched when we do that. Some people are good at doing that and some are not. So I think an easier way to do it is to actually consider that, okay, if the hydrogen is facing away from us, it's real easy. We just read it directly. We just go from 1 to 2 to 3 and say, is it going clockwise or counterclockwise? If we have the hydrogen pointing towards us, as we have in this case, what we can say is that, well, if we look from the back side as opposed to the front side, it's going to look like it's going in the opposite direction from either way. If we turn it around, it's going to look like clockwise is going to look like counterclockwise, and so on and so forth, if we're looking from the 2 different sides. So what we can just say is, since we know that, we can say that here we have it going from 1 to 2 to 3, and boy, that sure looks like it's going clockwise, which of course it is, but we're looking from the back side of it. So if we were to look from the front side, in other words, from behind the screen looking towards you, right now, you would actually be going counterclockwise, okay? And so since that's the case, what you do is when you see this and you basically say to yourself, oh, clockwise R, you say, oh, wait a minute, it's the opposite. So the opposite of R is S. I find actually this method of doing it to be less error prone than trying to visually turn it around in your head. Yes, a lot of times it's easy to turn it around in your head and visually. I can do that quite well because I'm used to looking at these structures, but I realize not everybody has kind of, has spent the time doing those types of things, and so it may be more difficult. So I think the other system where you basically say, if we're looking at it from the backside, that whatever it seems like it is, it's the opposite, right? So this is now in this case, going clockwise, so actually it's S because it's counterclockwise if we looked at it from the proper direction. I think that's just an easier way to do this when you have to analyze these. So you can do that for every one of these positions here. Okay, but I'll tell you another trick. And the other little trick, which is kind of handy, is once you've determined one of these structures, and you can see that obviously all of these are very related to one another, you can basically consider that, okay, let's just say I've figured out this structure. If you look at this one, you will notice that the structure way over on the left here is the mirror image of this. Why do I say that? Notice the backbone, right, is flipped around completely. The OH, though, right, is coming towards us, and it's coming towards us, right? The hydrogen here is coming towards us, Fluorine back, right? Hydrogen back. So that's as though we have a plane of symmetry going between these two molecules on this page, right? And they're mirror images of one another. So these two we know are enantiomers. What do we know about that? We know enantiomers, and this is an important point, have the opposite stereochemistry at all stereocenters, and this has two stereocenters. So we have to invert both of these when we take the mirror image of it. So R becomes S and S becomes R. So when we take the mirror image of this compound, instead of being 2R3S, it is now 2S3R. So you've saved yourself all of this work, right, just by recognizing that, oh, these are mirror images. Boom, we're done. Now, if we compare this compound to this compound, now this is easy. These two are oriented in exactly the same way, right? Our position 2, actually this is also, right, position 2 here in the chemical sequence, is in the same place, right? We have it over on the left side, and our fluorine is toward the right. Notice the orientation we have of this group is, here's our methyl, our hydrogen OH is coming towards us, the hydrogen is going back, and this other group, right, is to the right. So this is exactly the same orientation as this. So this 2R here is going to be retained, and it's still going to be called 2R in this, right? Again, we've gone through the same work, same priority. We don't have to do it again. We can see we've determined this already. This is identical to this, and so therefore we can call this one 2R. Now, we know this is oriented in the same way, right? We've already discussed that. But now we have this position here, this methyl is here, this carbon's here, so that's the same, but notice we've inverted these two. Here the hydrogen in front, here the hydrogen in back. Fluorine in front, fluorine in back. And remember, when we invert any two atoms in a chiral compound, we actually make the mirror image of it. So these have opposite stereochemistry. So this is 3S, this has to be 3R. So like I said, once you've determined one of these compounds, by inspection you can often go and then get the assignments of all the rest without going through all the rules for every single atom. So that's kind of a trick, that if you're doing a series of these like this and you have to differentiate one from the other, that you can save yourself a lot of time by doing this. Just make sure you get the first one right. Okay, that's, if you get that wrong, then you'll get them all wrong, right? So make sure you get the first one right. Okay, but the time spent in doing that will save you later on. Okay, now we have this compound. So now we know the stereochemistry is 2R, 3R. And we can see that this compound here is exactly the mirror image of this. You can just, by inspection, right? OH in front, OH in front, fluorine in front, fluorine in front, right? Same carbon chain, just flipped around opposite of one another. These are mirror images. And so therefore, 2R, 3R here, 2S, 3S here. Again, we have inverted both stereocenters to get this. So these two are enantiomers. Like we said, these two are enantiomers. Again, we're always comparing two compounds to one another. What does that mean then with regard to any other comparison? If we compare this compound to this, these are diastereomers. And what's a quick way to tell that? Well, this is 2s3r and this is 2s3s. So we've only inverted the 3 position, but we have not inverted the 2 position, right? We have not inverted every stereocenter. So if we have not inverted every stereocenter, we have diastereomers. We do not have enantiomers. We have to do every stereocenter, right? Like 3s, 2s, right? 2r, 3r. Both stereocenters are inverted. Just like the comparison of this, 2s, 3r, 2r, 3s, both centers inverted. So these two are enantiomers, these two are enantiomers, this versus this is a diastereomer, this versus this is a diastereomer, right? This versus this is a diastereomer, and this versus this is a diastereomer. So I hope that's clear. Okay? Now, Con-angle Prelog system has more than just these 5 rules. It's a longer list. But what we do in this, in order to determine the particular RRS configuration, we go through these rules until we get to the point where we can actually determine the configuration. What these additional rules are, as we go down the list, are to take care of ambiguities where we have not yet determined which group has priority over another. Okay, so let's start out with this, right? Substituential list in order of decreasing atomic number. Okay, we've talked about that. When 2 or more atoms are connected to an asymmetric carbon that are the same, then the atomic number of the second atom determines the order. Tree graphs, right? So this is what we talked about in the previous slide, right, where we had 2 carbons that were the same. The tree graph, you know, this is not drawn in the same branched way, but the idea is that we are now looking at the next atoms that are attached to that ambiguity point, the ambiguity point being we don't know the priority between these two, right? And we look for the atom that's attached to those that has the highest atomic number, which in this case is oxygen. Okay, so that's what this next rule has to do with. And we keep doing that over and over, right? Let's just say, and we're not going to give an example here, but let's just say these, let's just say that instead of this was an OCH, right? That this was also an OCH, right? So for example, this here is an alcohol, and we had an alcohol coming off of this, right? And we had another extension of another carbon again. Well, we'd have to basically then say, well, these two are identical, and we'd have to figure out where do we branch off to determine the next priority. So obviously the oxygens are the same. We're not going to get differentiation there unless the oxygens are different. So if one was an ether versus one was an alcohol, then we could use that as a branching point. Otherwise, we'd have to look at the carbons if that was the case. Like I said, you know, this can get complicated. You can get things that are, you know, you have to go many steps out in order to determine it. But most of the time, you don't have to go very far. You know, 1 or 2 of these steps out is usually all it takes for most molecules. Okay. All atoms that we're considering are considered to have a valence of 4, right? So we're going to always consider that there are going to be 4 things attached to it. And if for whatever reason the valency of the atom that we have has less than 4, we'll consider that it has the other two basically phantom atoms, in other words, where bonds would be, have an atomic number of 0. So some examples of this might be an oxygen or a sulfur, right? Because they have 2 lone pairs of electrons. Normally we consider the valency of these to be 2, not 4. So those would be examples where this might take place. Isotopes of greater atomic weight take precedence of those over lower ones. Okay, so this is something that people have actually made use of in order to look at enzymatic characteristics. There's a variety of things that are important. They can make chiral compounds containing isotopes such as deuterium versus hydrogen, and put this in one or the other position in a case where a compound is what we call prochiral. Prochiral means we have something like a CH2, right? Well, 2 hydrogens is going to be symmetrical, so therefore it's not chiral. But if you have a situation like that where if you change the priority of those 2 hydrogens, in other words, make one a deuterium and one a hydrogen, well, you can have 2 stereoisomers of that, right? The deuterium could be in one position, or you could flip the 2 and it can be in the opposite, and then you can have mirror images of one another. So those 2 hydrogens, when you have them on there in a prochiral compound, they're actually called pro-R and pro-S. And if an enzyme does chemistry at one of those position like that, usually it does it in a stereospecific fashion. And so what group is substituted or where it comes in is it deals with or changes either the pro-R or the pro-S proton. Okay? So we can use this feature to actually look at enzymatic structure, structural preferences, mechanisms, and things like that. And I'm not going to get into the details of how those experiments are done, but it's where we use this type of stereochemistry nomenclature in compounds where isotopes occur. And this is the most common way, usually deuterium and hydrogen type compounds. Now, double bonds or triple bonds are treated as though they are bonded multiple times to that atom. So if we have a double bond, a carbon, double bond to something, it's considered as bonded to a carbon and then a carbon again. Okay? That's how we determine that. So why would that be important? Well, let's just say we had a very symmetrical looking molecule. On one side there's a double bond and one time there's a single bond, right? And the single bond is to a carbon, but on the other side it's a carbon with a double bond. Well, the double bond gets priority because it's attached to 2 carbons, whereas on the other side it's only attached to 1 carbon, and presumably the other groups would be hydrogens, right? And so it'd be a carbon and 2 hydrogens, and this would be a carbon and a carbon and a hydrogen or whatever. But I mean, the point is it would have 2 carbons. This would only have 1 carbon in lower priority atoms. So again, this would get the greater priority. So this is how this rule works, and they all work together in order to try to get to the determination. Like I said, there are additional rules beyond this for situations that if these rules do not completely give you an answer, other rules may tell you what to do in those situations. Okay, but we don't need to get into extremely complex situations like that. There's a lot of things having to do with symmetry. There's if you have 2 substituents that are both chiral and identical, right? The R takes precedence over S. There's all kinds of things like this. I don't really expect in my classes at this level to know those later rules and that level of detail, just to very simply be able to call something R and S for pretty standard molecules. Okay, so for L amino acid, we have a stereochemistry that is based on this common type of amino acid structure. So we have, if we draw our amino acid in a way where we have our nitrogen, C alpha, which is this carbon, that's where the branching occurs, and then C prime, which is the carbonyl carbon of the amino acid. Our R group goes back and up in the L configuration. Now, in most cases, these are carbon substituents here, and they're attached to other things like in serine it'll be an alcohol, in alanine, right? It's just hydrogens. In other longer chain amino acids, there are other carbons. Okay, all of those situations, they will have S stereochemistry here. Okay, and that has to do with priority is going to be the nitrogen, the carbon that's attached to 3 oxygens, right? Because it's C double bond O and then another oxygen, right? Or if it's in a peptide chain, right, it's a C double bond O nitrogen, right? So in either case, that will have the next priority. Hydrogen, of course, is the least. And then this position would then be the third. So it would go counterclockwise, and it's S. Now, there's only one amino acid in the 20 natural amino acids that's different. And that's if we have cysteine. In cysteine, this R group is a CH2SH. So we have a carbon here and a carbon here, and this is attached to 3 oxygens, but this is attached to 2 hydrogens and a sulfur. Sulfur has a higher atomic number than oxygen. So even though there's more oxygens here, it doesn't matter. Sulfur has a higher atomic number. So the priority switches, and now it's 1, 2, 3. So in cysteine, our L amino acid, right, is R. That's the only amino acid that has the R configuration. So just to be aware of that, we can't say all L amino acids are S. Most of them are, but there is that one exception because of the sulfur. So again, these rules are not interchangeable. They're determined by different methods, and that's just another example of that. In the case of here, our L-serine, what natural compound was this compared to in order to get to the determination of what it looks like and what its orientation was, right? So L-glyceraldehyde was the standard compound from which it was compared. You can imagine the interconversion of groups here, right? Hydroxyl to an amino. We had the CH2OH, clearly that's the same as the CH2OH here. And aldehyde versus carboxylic acid, that's just a difference of one step in an oxidation state, oxidation reduction, or oxidation in this case. So that is where the L configuration name comes from. It's from this original L-glyceraldehyde determination and the comparison. Now again, this is just showing some examples of enantiomers. We described what they were, very simply, non-superimposable mirror images, or compounds where every stereochemical center is inverted. In this case, we have one stereo center here, and in this case it's S, and in this case it's R, right? They're inverted. The methyl group you can see is flipped from front to back in these two comparisons. Now, this is actually kind of interesting, and it's important because in drugs, what does the stereochemistry do for us? Well, this is the naproxen that is sold as a nonsteroidal anti-inflammatory drug. This R-naproxen is not active, and so it is not sold. In fact, in the manufacturing process, it's made as a racemic mixture, in other words, a mixture of both of these. And these are esterified, so this carboxylic acid becomes a carboxylic acid ester, and then an enzyme is used to hydrolyze it. Now, the enzyme only recognizes one of the two forms. And then when you do that, so one stereoisomer will be an ester, one stereochemistry will be a carboxylic acid. They're very easy to separate from one another, and now you have stereochemically pure material. So that's actually the manufacturing process for how they resolve the two of these from one another and get the pure S-naproxen. Now, as it turns, the S is dextrorotatory and the R is levorotatory, but again, there's no necessary correlation between these two. You will find R compounds that are both either levorotatory or dextrorotatory. So that doesn't determine which way it rotates light. That's just two different systems for identifying a particular isomer. This down here is showing levorphenol versus dextromethorphan. So this is an over-the-counter drug cough suppressant that you can just go to your local store and buy very easily. It's very effective. It binds to a receptor that's completely different than levorphenol. Levorphenol binds to opiate receptors and has its actions. This binds to a completely different CNS receptor. Okay, and actually in excess this is a dissociative, so sometimes it is abused in that way as a dissociative agent. Ephedrine and pseudoephedrine are examples of diastereomers. It has two stereocenters. Notice in ephedrine it's 1R2S, and in pseudoephedrine it's 1R2R. So as it turns out, this position here, this position is considered 1 here, the way this is numbered, where the OH is very important for activity and potency in these types of compounds. Okay? So that being the case, both of these compounds share that, where this methyl group has some effects on the activity of the compound, but they both act on the same nervous system as each other. They have slightly different effects. Pseudoephedrine is still sold as a decongestant. Geometric isomers. So this particular drug, right, has a double bond in the middle of it. If it is in this Z configuration, right, so now here it's a little more difficult to say, oh, wait a minute, is this cis or trans? You can do it. And you would use rules of priority for naming cis and trans isomers and E and Z isomers, pretty much very similarly. But the point is that this one's not quite as obvious to see, well, which one would be which. So if you use a systematic nomenclature, this turns out to be the E. And what it's comparing, so what is it, this kind of like trans, right? E is trans. It's comparing this group here in relationship to this group here, right? And that's going to be based on priority rules for this ring versus this ring. And then, of course, the hydrogen versus this. This is clearly the larger. So that being the case, it's looking at this pyridine ring versus this chain as a cross on the opposite side of that double bond. Now, again, when we talked about stereochemistry and biological activity, we can have these chiral centers that have 4 different things attached to them. Biological selectivity is based on the fact that you have a chiral compound over here that has sites that interact with these portions of the atoms or things possibly attached to them, right? This is a bit of a cartoon and a simplification. But you can see that A goes into A prime, B goes into B prime, and C goes into B prime, and it fits like a little puzzle, right? Now here we have A, B, C, D, and it's not necessarily completely obvious, but these, it turns out these are mirror images of one another, so they're the opposite stereochemistry. But our receptor is still the same here. So our compound of the opposite stereochemistry, we can say, well, let's try to fit B and C in the holes. Yeah, we got it. We lined them up. But if we try to do that, we notice the D is over here and not A. Well, wait a minute. That's a mismatch. That's not good. And you can play around with this all you want. You can say, well, let's not match up B and C. Let's match up A and B. If we do that, what do we get? We end up with D over here and C going up in the air, right? So what it amounts to is we have interchanged 2 of these groups, right? In this case, say, for example, A and D, and that's what has ended up giving us the mismatch. So this is a very important slide, and you should know these aspects of what does stereochemistry affect with regard to biological recognition. So it is important in the recognition at the target receptor, resulting in differences in bioactivity, right? We showed some examples of drugs where one isomer is what's used and the other isomer is not, right? Like naproxen. Recognition by non-target receptors can result in differences in side effects. So in other words, we can have our main drug, right, which binds with best affinity to its target receptor, and it may or may not have some, minor affinity, right, to other receptors in the body, but it's generally less in most cases, right? If we're using something as a drug, usually there's a reason for it to be more active than it is causing side effects, right? So it has some selectivity. The opposite isomer, right, may be completely devoid of any effects, or it may recognize completely different targets that we didn't intend to be hitting, and that can lead to side effects. So that's a case where the mirror image, right, the enantiomer, is not what we would call innocuous. In other words, it's not like as though, well, we can just double the dose, right, and get to the same amount of proper isomer, and then the other stuff doesn't do anything. Well, no, it doesn't necessarily not do something. It can do stuff in the body that we don't intend. It's certainly not doing the action that we do intend, so why give it? It's only going to cause problems, right? So that's another important aspect. Recognition by metabolizing enzymes can result in pharmacodynamic differences. So what does this mean? Metabolizing enzymes are kind of like receptors, right? They recognize molecules and they cause some type of chemical reaction on them, either a transformation of a functional group or they attach something, right? That's phase 1 or phase 2 type of metabolism. But they do so in a fashion that recognizes these stereospecific structures because the enzymes themselves are composed of amino acids. So what does that mean? If we change the stereochemistry at a particular position, right? Let's just say even if they both have activity, one might say, oh, that's pretty good. We can use the mixture on that basis. But what also may happen is one enantiomer might be metabolized quickly and another one might be metabolized differently. And that could lead to potential issues from the standpoint of we're going to want a understandable and predictable metabolism to take place because we want to know how to dose the drug and we want to know how it's eliminated from the body. So in that case, if both were good as the drug, right, and they have two different metabolic profiles, there's probably one that would be more desirable than the other, and then that single isomer would be better to give by itself than the mixture again. Okay? And then the other aspect is our physical properties and recognizing by tissues that affect ADME. So what are we talking about? So metabolism we just talked about, but we do have absorption, distribution, and elimination are the other parts. That's what the ADME means. Absorption, distribution, metabolism, and elimination. Now when we talk about absorption, we can have passive diffusion. Now and generally the stereochemistry is not going to be as important there. But if we have any type of an active transport system, and if it's interacting with proteins in any way, right, then absorption can be different. Also, as things are absorbed, there are metabolizing enzymes, right? So their ability to be absorbed may be different based on differences in metabolism. Distribution, the same type of thing from the standpoint of, getting across the gut is just one step. How it gets to other tissues in the body is another. And again, it's going to possibly interact with proteins like albumin in the blood and everything else, blood-brain barrier, various types of transport systems to be able to get across the blood-brain barrier into the CNS. So that's a distribution. And then we have elimination, and that has to do with then when drugs are eliminated, let's just say by the kidney route, they basically all get filtered out, but then some of them get reabsorbed, right? And so if there's differences in the stereochemistry of the compounds, they could be reabsorbed potentially differently, again, leading to a different profile for the drug. So that's the important parts you need to know about all of those topics. And there are additional slides here. They are more for informational purposes. This is just an example of what we were talking about with a meso compound. This has stereochemistry up here and stereochemistry down here, but notice we have a plane of symmetry between the two halves of the molecule that otherwise have the same functional groups. So if you look at that, if you were to take a mirror image of this compound, what would you have? What's the mirror image? Well, you could draw this same type of thing and just switch where the hydrogens and OHs are. So if we do that and take the mirror image of it, so now what we have this same compound, but the OH and the OH here on the right side and the hydrogens are on the left side. Now take this whole molecule, right, that we just created over here and turn it 180 degrees. So we take this carboxylic acid and we turn it up here and we take this one down here. What does it do? Well, what's going to happen? This OH is going to end up way up over here. This OH is going to end up down here. This hydrogen, right, is going to get rotated around up here, and this hydrogen is going to get rotated around down here. So in other words, if we take a compound where we have the OH here and the hydrogen here, right, which is the mirror image of this, what we're going to do is we're going to take that compound with the OH and rotate it down here where the OH in this one is. And the same thing here. The mirror image has the OH over here, and that OH is going to rotate around and be up here. These two carboxylic acids are identical. So what we've done is, even though we have the mirror image molecule, if it rotates, it's superimposable. Right? So what did we basically say? We have enantiomers when we have non-superimposable mirror images. Here we have a compound that has chiral centers, but if we take a mirror image of it, it is still superimposable. So based on that, if you remember the previous slides when we said meso compounds are achiral, which means not chiral. They have stereocenters, and we can define the stereochemistry, but it's not considered a chiral molecule because we can't make a true enantiomer of it, right? The mirror image is indeed itself because of this additional plane of symmetry. So that's why we're not going to make too much about meso compounds, because in a sense, them being achiral, we don't have these issues that we talked about for stereochemical isomers, right? It doesn't exist because it's only one compound. It's not two enantiomers. That's exactly what we're talking about. These other things we have here, this are just different types of nomenclature. Erythro, threo, again, not a priority at this level, but it's only being put on these slides just so the material can be referred to. So here we have enantiomers, right? We have 2s4s, 2r3r, so this is normal, right? And then when we have meso compounds, now this is a more complicated meso compound. This one has 3 stereocenters. These things are meso compounds because they do have this plane of symmetry, and when you basically take the mirror images, that they're the same compound, right? These are 2 different ones, and so we can differentiate it here. So what's with this small r and this small s? It has to do with, if we do the priority rules, okay, if we have a branch, and in this case, this branch where the 2 is, versus the branch where the 4 is, and they have different stereochemistry, R gets priority over S. In this case, here, right, we have the 2 position, which is R, and we have the 4th position, which is S, right? This would get priority over that. So why is this one different than this? Because the OHs are on the opposite side, right? So one's going to end up looking like an R and one's going to end up looking like an S. So again, nomenclature can get very complicated. These again are both a chiral compound, even though we do have a system for naming the centers. Sugars. Now this is important in biochemistry and a variety of things. You'll see a lot of these names. D-glucose, right? Beta-furanose or pyranose, right? 6-membered ring, pyranose, 5-membered ring, furanose. Here, the alpha beta has to do with this anomeric carbon. So if you open up this ring here, you have an aldehyde, and in this case, it's a hemiacetal, right? So it's a hemiacetal where it either points up or down. Stereochemistry is different in these, and we also give them different names, right? So if it's pointing down, it's called alpha. If it's pointing up, it's called beta. Just sugar nomenclature. And then, of course, this is for the pyranose and then the furanose. Here we see the interchangeability between these, right? Because these hemiacetals can open up into the aldehydes and alcohols. So we can see here it's 1, 2, 3, 4. It's on the 4th carbon. So here it's 1, 2, 3, 4. So it's this OH, right, that is here in the furanoses. Whereas it's on the next carbon down, this alcohol, for the pyranoses. And when we link these together, there's nomenclature for this. I'm not going to cover it, but this is just showing some examples. We have everything from our alpha, our D stereochemistry. Then we have which positions are linked to one another to then another sugar, and then it's linked again to another sugar, and so on. If they're just linearly linked, it's simple. This one is actually branched, right? You have 2 different sugars off of one, hence that's where this brackets nomenclature comes from. So again, this can be rather complicated, and it's not the scope of this course to cover all of this. Conformational isomers, this relates to this flexibility aspect, which becomes important in particularly peptides. We do talk about it a reasonable amount. So if we do crystal structures, right, we get Cartesian coordinates, but another way of defining a molecule is like by a roadmap, by basically saying we start with one carbon and then we go to the next, and we need to turn the bond by a particular direction to get to the next carbon, that type of a thing. So a torsion angle is nothing more than this, where again we're looking down a bond, in this case the bond between here and here. This ABC, right, forms a tristar right in front, and the way this Newman projection is shown is that we draw a circle that obscures, right, the bonds that go to the back, but we can still see the back trident, right, but it's not confused with the ones in the front. That's what this basic projection is about. And if we go from turning A to X, right, and go in a clockwise direction, that's a plus 180 degrees, right, going all the way around a 360, right? So going from A to Z is 60, 120, right, A to B, and A to X is 180, and so on. If we go A to Y, right, that's minus 60, minus 120 A to C, and minus 180 and plus 180 are identical, right? Okay, other things you may run into is gauche. We have gauche plus and minus. So again, it's based on the torsion angle, either turning to the right or to the left. Trans is another way of saying 180 degrees. It can get more complicated. We can talk about these as much as basically the relationships of 0 to 30 degrees, 30 to 90 degrees, 30 to 150. And we can basically call these things names. Again, complicated, but if you ever see the terms, you realize, okay, we're talking about torsion angles, and there's a definition I can look up at that point to figure it out. Cyclohexane conformations, we already talked about it, but the large things that we talk about is if it's coming up or down from the ring, just directly, we call those axial. If it's kind of coming off in a more straight direction off the side, we call that equatorial. Okay, and we can twist these rings either completely into what looks like a little boat here, or we can get halfway between these two and we get something which is called a half twist. D-glucose is, again, it's not, we draw it like this often, but really what it is, it has these two different type of chair conformations. As it turns out, one is preferred to the other. The one where this CH2OH is equatorial versus axial is preferred, but it can interchange between the two. So this last bit of nomenclature relates to these chair conformations for these dihexoses, where in this case we can have two forms. The preferred one is one where the last CH2OH is equatorial as opposed to being axial. Right, hence that's depicted by this difference in the arrows here. And when we have this case here shown on the left, right, where our 4 is kind of going up here, in this case, we're calling it a 4C1 chair. And this is the one where our 5 position, the CH2OH is going to be equatorial. If we flip it to the other type of chair, right, where this now is going down, and we call this a 1C4 chair.